Alright, gang. Here we go. Last part of the unit. Some people said it couldn't be done, but then we did it and we stuck it to them. Alright? So calculating freezing point depression and boiling point elevation. So remember, we talked about colligative properties the last unit, talking about how when you dissolve things in your solution, it makes the freezing point drop or the boiling point go up. So now we're going to talk about how to calculate exactly how much it goes up or goes down. All right, here's your two formulas that you need to know. Notice that they're very, very similar to one another. Whoops. All right. So we've got the delta T, that's the change in the temperature. Notice the F is for freezing. It's equal to the K value. Okay, so that's a constant for the solution. For water, it's a certain value. If you have a different solution like methanol or toluene or methylene chloride, okay, it's going to be a different value. Okay, we're only going to be using water, and I'll just give it to you. Don't worry about memorizing it. Okay, now this guy, so this is a constant. Okay, constant. All right, now this guy here, notice the cursive italicized M. That's your molality. Remember molality? Yeah, this is why it's important. So molality is used here because remember, molality is in moles per kilograms of the water. Okay, now think about this real quick. If you raise your temperature and you get close to the boiling point of water, your volume actually goes up a small amount. Because it's gone up, your concentration has actually gone down. So we can't use molarity in this formula because molarity is not going to work because it changes when you get close to the boiling point or freezing point of whatever substance you're talking about. So we have to use molality. Okay, molality uses kilograms. When you get something really, really hot and close to its boiling point, it's going to weigh exactly the same amount as it did when it was at room temperature or really, really cold. The mass does not change as it gets hotter or colder, but its volume will. Okay. All right, so we use molality, moles per kilogram. So that's why we talked about molality before. And this last one, this I value, remember this is your Van't Hoff factor. All right, so this is how many particles it breaks up into. All right. Boiling point elevation works exactly the same way, but we're going to have a different constant. Okay, but it's still got molality and the Van't Hoff factor. The biggest thing between these two things is remembering that it's freezing point depression. Okay, so whatever you calculate here, this is going to make your temperature go down. Whatever you calculate here, this is going to make your temperature go up. All right, so when you're calculating freezing point depression, you had better get a negative degree Celsius. All right, and when you get this, okay, so it should be below zero. When you do boiling point elevation, you had better get an answer that is greater, oops, I fouled that up, greater than 100 degrees Celsius. Whatever answer you get, all right, should be greater than 100 degrees Celsius. All right, so antifreeze protects a car from freezing. It also protects it from overheating. Calculate the freezing point depression and the freezing point of a solution containing 100 grams of ethylene glycol, and that's antifreeze, and 0.5 kilograms of water. All right, so delta T F is equal to Kf times the molality times the Van't Hoff factor. Okay, well, Kf, they give it to us right there. All right, that's good. So now we need the molality. All right, so molality is equal to the moles over kilograms of water. All right, well, so we've got 100 grams. So we got to convert our ethylene glycol into moles. All right, so ethylene glycol is 2 carbons, 6 hydrogens, and 2 oxygens. All right, we're going to add those guys up. So we got 2 times 12.01. We got 6 times 1.01. And we have 2 times 16. All right. 2 times 12.01 plus 6.06 plus 32. So I got 62.08. All right, so that's our moles. Okay, so we're almost there, right? That's our molar mass. That's grams per mole, right? Okay, so we've got 100 grams of ethylene glycol. We got to convert that into moles, so we're going to put grams in the bottom, moles in the top. We're going to put Witten with moles, and our molar mass is 62.08. We're going to put that in the bottom. So 100 divided by 62.08, 0.08, and we get 1.61. Okay, and remember, this is not our final answer, so we're not going to worry about sig figs here. We're just going to let that guy ride, and I'm going to write it out to a couple extra decimal points so I don't get any rounding errors. So 1.6108. Okay, so that's our moles. All right, so that's the number we're going to put in here, 1.6108 moles. All right, per kilograms of water. So that's going to be 0.5. All right, because they've already converted us. That's really nice of them. So if we divide that by 0.5, I got 3.22. Again, this is not our final answer, so I'm not going to round. All right, 165. All right, so that's our molality. All right, and then finally our Van Hoff factor. Now ethylene glycol, this is molecular. Right, this guy here is molecular, so it's got a Van Hoff factor of 1 because it doesn't have any cations or anions, so it's not going to break up into anything. So our Kf is 1.86. All right, our molality is this guy here, 3.22, 165, and our Van Hoff factor is 1. All right, so we're going to take 1.86 times our molality times 1, and I got 5.99226.9923. Alright, so now let's think about sig figs. So this guy, let's just assume this has a decimal point in here, because why not? Okay, so that's 100 grams, and this is 0.5, so they both have 3. So we're going to round to 3 sig figs, so this becomes 5.99 degrees Celsius. Alright, so our freezing point depression, this is our freezing point depression. We'll call it FPD. All right. So that's how much our temperature went down. So to find the new freezing point, okay, because it asked for the freezing point depression, we found that, and now we also need to find the freezing point. So in order to find the freezing point, we're going to start with our freezing point of water, which is 0 degrees Celsius, and we're going to subtract how much it went down. It went down by 5.99. Okay. So our new freezing point is really, I almost punched that in my calculator. How silly would that have been? Negative 5.99 degrees Celsius. All right, so that is the temperature at which our antifreeze will be able to freeze our water. Or that's the temperature, the new freezing point of the water in our engine. Okay. Last example. Here we go. What is the boiling point of a 1.5 molal sodium chloride solution? Oh, they calculated molality for us. How nice was that? Okay, so our delta TB, okay, is equal to Kb times molality times the Van Hoff factor. All right, so we've got Kb. Kb is right here. We've got molality. It's right here. And we've got our Van Hoff factor. Well, this is sodium chloride, so this has a plus, this is a minus, so it turns into 1 sodium and 2 chlorines, so its Van Hoff factor is 2. All right, so Kb is 0.512, the molality is 1.5, the Van Hoff factor is dose. All right, so we get 0.512 times 1.5 times 2, and I got 1.536. Okay, now let's talk about sig figs here for a moment. 1.5, we'll write this down before we forget. 1.536, okay, degrees Celsius. So this guy here has 3 sig figs. This one has 3, and you might say to yourself, oh, that's got 1. But remember, how did we get that number? Well, we figured out how many ions this would turn into, and we counted to 2. Ah, we counted. Remember, counted numbers have infinite sig figs. Because we've counted them, we know there's exactly 2. So this does not affect our significant figures because it's counted. So our answer should have 3 sig figs, so it becomes 1.54 degrees Celsius. Okay, so our temperature, remember this is boiling point, okay, boiling point elevation. All right, that's the key. We're figuring out how much our boiling point is going to go up. So if we started at 100, okay, we went up by 1.54. So we're just going to add 1.54 degrees Celsius to here. So it becomes 1.54 degrees Celsius. So our new boiling point, when we've added that much water to our solution, is 101.54 degrees. All right. So that's how you calculate freezing point or depression and boiling point elevation. Congratulations, we made it through the unit. Do some practice problems. Come take your checkpoint.